Question number 11. Two uniform rods A and B having same dimensions but made of different materials of density dA and dB. Rotate as shown in the figure. If the rotational kinetic energy of the rods are same, the ratio of angular momentum of A divided by angular momentum of B is given by. They have given that there is the same kinetic energy, same rotational kinetic energy. Then we can write half IA omega A squared equals half IB omega B squared. I mean moment of inertia of object, omega is angular velocity of object. Now we have to get the ratio between angular momentums of A and B. Angular momentum means product of I omega. Then I will cancel out half. Then I will subject IA divided by IB. No, I will subject omega A divided by omega B. Omega A divided by omega B is IB divided by IA square root. Moment of inertia I is directly proportional to mr squared. R is depending on mass distribution. Now there are same dimensions for both objects, therefore this value is constant. We can get I directly proportional to mass, and we know that mass equals density into volume, therefore mass is directly proportional to density. When getting these two relationships, we can get I directly proportional to density. Then we can write this relationship omega A divided by omega B equals to density of B divided by density of A. Now we have to get moment of inertia because of we have to get IA omega A divided by IB omega B ratio. Now we have obtained omega A divided by omega B ratio, this part. We have to get IA divided by IB. When getting IA divided by IB, we can get that IA divided by IB equals to moment of inertia is directly proportional to density, therefore we can get dA divided by dB. Now there are two relationships. When getting this relationship, we can multiply this part and this part. Then one root dB term is cancelling. We can get dB divided by dA root multiplied by dA over dB. Then cancelling this part and this part, we can get root dB. We can cancel out root dA, then answer is root dA. Root dA divided by root B means dA over dB root. They have given with power, then we can get this answer as dA divided by dP to the power half. Then answer is dA divided by dB to the power half. Answer is 4 for the question number 11. So question number 12. Three wheels A, B and C are same masses and same external radius are made out uniform sheets of different materials as shown in the figure. These wheels are released simultaneously from rest from the same height at the top of an inclined plane. The wheels roll down without slipping. They order that they will reach the bottom of the inclined plane as first, second and third respectively. There are same masses for all three objects. Therefore, when considering moment of inertia, we have to compare mass distribution. And we know that the maximum mass distribution is for A because of it is like a ring. the minimum mass distribution for B, it is like a plane object. And then we can get order of moment of inertia. IA is the maximum value. Moment of inertia A, then IC and IB. We know that when rotating an object, if the moment of inertia is a higher value, then it can't change angular velocity easily. Therefore, this object IA is increasing its angular velocity slowly with compared to B and C. Therefore, it will take maximum time to reach the bottom. Then we can get order time A, TC and TB. Time A, time C and time B should be the order of time taken to come to the bottom of the inclined plane. Then now we have to get first, second and third respectively. Therefore, we have to get B is coming first, C is second, A is final, last one. Then BCA, answer is 2 for the question number 12. Then question number 13, a uniform circular disc of radius capital R and capital M rotates with a uniform angular speed omega in a horizontal plane about an axis, passing through its center perpendicular to its plane. The moment of inertia of the disc about axis described about is half mr squared. Then a ball of clay, mass m weight, placed gently on edge of the disc, and if it is sticks, the new angular speed of the system is. Now we have to consider first one. There is a circular disc. Its moment of inertia is half mr squared. It is rotating with omega angular velocity. And for the second situation, there is a point mass at the edge of the object. Now, moment of inertia of circular disc half mr squared, it is not changing. We have to consider moment of inertia of this clay particle. It is a point mass, then its moment of inertia is mr squared. But mass is given as m over 2, m over 8 r squared. Now we can use conservation of angular momentum because of there is no external unbalanced torque on the system. For the first situation, we can get I omega, I1 omega 1 equals I2 omega 2. Moment of inertia of first object half mr squared into angular momentum omega should be equals to, for the second situation there are two moment of inertia values. We have to add half mr squared, it is the moment of inertia of circular disc, plus this is the moment of inertia of point mass, m over 8 r squared. This is the total moment of inertia. We have to multiply by the angular velocity, final angular velocity. I have considered it as omega dash. Then we have to simplify half mr squared omega. We can get 8 as the least common multiple. Then 4 over 8 plus 1 over 8, 5 over 8 mr squared omega dash. Now we can cancel out mr squared. 2 divided by 2, 1, 8 divided by 2, 4. Then we have to subject omega dash. Omega dash equals 4 over 5 omega. 4 over 5 omega then we can get third one is the correct answer for question number 30. Then question number 14. The circular disc shaped wheel type firework shown in the figure performs a rotational motion about the z-axis on the horizontal smooth floor due to a constant reaction force generated by its burn. Assume that the pin wheel follows the shape of uniform circular disc and throughout, and its moment of inertia half mr squared. And about z-axis, if m, r, omega and alpha are the value of masses, radius, angular velocity and angular acceleration respectively, if the burning pin wheel at certain instant, then we have to consider given expressions. For the firework, they have given that there is a constant force. They have given that there is a constant force, constant reaction force gently generated by burning. Therefore, we can write tau equals psi alpha. We can get torque as force into radius. Force into radius because of when considering this firework, if the force is F, we have to multiply by radius to get the torque around this axis. Should be equals to, we can write moment of inertia half mr squared, we can consider it as a circular disc, half mr squared alpha. Now we can cancel out one alpha term, F equals half mr alpha. Now half is constant, therefore we can consider when reaction force is constant, mr alpha should be constant. Then mr alpha should be constant, it is the answer. Answer is 1 for the question number 14. Then question number 15. The two uniform discs A and B shown in the figure are made of the same material and have equal masses. The radius of disc A is greater than that of B. The discs are kept in isolation at outer space. Consider the following statements. Part A. The disc A takes a long time than B to gain a given speed under an external force acting through the center of the disc. In part A statement, they have given about linear motion. There is a force, we have to find the time taken to get a constant speed, given speed. The linear velocity, linear motion is not depending on radius, it is depending only on mass of the object. Therefore, there are same masses for same material and same masses for both objects. Therefore, there is no time change. Then we can get A is incorrect. Statement A is incorrect. Then statement B. The disc B takes longer time than the A to gain a given angular speed. Now we have to consider rotational motion. Then when considering rotational motion, radius of A is greater than radius of B. Therefore, we know that moment of inertia is half mr squared. Radius is greater than for object A. Therefore, moment of inertia is greater than for object A. Then the object A is changing its angular velocity slowly than B. Therefore, time should be greater value for A. Then B also incorrect. Statement B is incorrect. Then statement C, the disc B has higher rotational inertia about its axis know radius of A is the greater value, therefore A has the maximum, A has the higher rotational inertia, moment of inertia. Then all statements are false. We have to consider 5 is the correct answer for question number 15. Question number 16. Starting from rest a sphere takes a time t to roll down a rough plane. If plane is made frictionless, its time taken by the sphere to slip down will be. Then considering first situation, it is a rolling object. We have to consider increasement of rotational speed and increasement of angular velocity and increasement of linear velocity. But for the second situation, it is slipping without rotating. Therefore, we have to consider only increasement of velocity. We know that potential energy of the object is converting to kinetic energy for both situations. Therefore, the speed of second situation should be a larger value. The speed is a higher value, then time should be lower than t. Then the answer is 3 for the question number 16. Question number 17. As shown in the figure, a child sitting on a rotating chair rotates with angular speed omega. The moment of inertia of the system with the child around its axis of rotation is 2 kilogram square meters. As shown in the figure B, while rotating, the child catches a ring B of mass 4 kilogram and diameter 1 meter, which is falling vertically with its plane horizontal and with no angular momentum. If the final angular momentum of whole system would be. We have to use the conservation of angular momentum when considering first situation. We can use I1 omega 1 equals I2 omega 2. For the first situation, they have given that angular moment of inertia is 2, angular velocity omega. For the second situation, we have to consider moment of inertia of child with rotating chair 2. We have to add moment of inertia of a ring. It is mr squared. Mass of wheel is 4, radius is half, because of they have given that diameter is 1 meter. Then half square. We have to use mr squared. Mass into radius to the power 2. We have to multiply by final angular velocity. I have considered that final angular velocity is omega dash. Then we can simplify 2 omega equals, when simplifying this value, answer is 1, 2 plus 1, 3 omega dash. Then omega dash is 2 omega over 3. 2 omega over 3. Answer is 2 for the question number 17, when finding angular velocity. But they have given that find the angular momentum of the object. There is a problem with given question. Therefore, they have given that all marks for the question number 17. But we can calculate angular velocity of the object without using angular momentum. Angular velocity is 2 omega over 3. Then we can get answer is 2 for the question number 17. Then question number 18. A decoration consists of 4 independently rotating sets of small lanterns P, Q, R, S, which are fixed to a rotating central pole as shown in the figure. Figure A. All rotation takes place around vertical axis. Which of the following modes of rotation provides best stability of the entire decoration? When considering the stability of rotating system, the momentum should be, angular momentum should be a greater value. Therefore, all lanterns and middle axis should be rotate in the same direction. Then we can get 4 is the correct answer for question number 18. Then question number 19. The figure shows a bicycle wheel which is rotating with large angular velocity. We have to remember that there is a large angular velocity. About the axis, AB hung from starting string connected to the end A folding from end B. If it is released from end B, then we have to consider the movement after releasing. Angular velocity. There is an angular velocity for the rotating wheel. Therefore, it should move such that the axle wheel rotates about vertical axis through A while AB remains approximately horizontally. There is a weight for the wheel, therefore there will be a small inclination, but approximately horizontally. Then answer is 3 for the question number 19. Question number 20. The moment of inertia of a certain spinning star has dropped in 1/3 of initial value due to the contraction. The ratio of new rotational kinetic energy of star divided by initial rotational kinetic energy of star is equal to. We have to consider the kinetic energy. We know that kinetic energy of star half I omega squared. We have to get ratio between half I2 omega 2 squared and half I1 omega 1 squared. We can cancel out half. Moment of inertia is 1/3 of initial value. It means if the moment of inertia for the first situation is I, final situation I over 3. Then moment of inertia is 1/3, angular velocity should be 3 times according to the conservation of angular momentum. Then if the angular velocity for the first situation omega, angular velocity for the second situation, final situation 3 omega. Then we can substitute values I over 3 omega, I over 3 into 3 omega squared divided by I into omega squared. We can cancel out I and omega. Then 3 squared 9, 9 divided by 3, 3. Then our ratio should be 3. Answer is 3 for the question number 20.